Okay, I think we are on time now. So, good morning, good evening, good afternoon, everyone. So, I'm Philip from the Chinese University of Hong Kong, and I'm the host of today's webinar. So, we are very honored to have Professor James Evans from Chicago Department of Sociology, who is also the director of the Knowledge Lab and an external professor of Santa Fe Institute. James is a renowned expert in sociology and computational social science. So he will be sharing us with the topic of rediscovering and redesigning the social world in the age of AI agents. So James, you have about 1 hour, including Q&A for all the participants. If you have any questions, you may either raise your hand in the Zoom or you can type in the dialogue so that I can hand it over to James. Okay, the floor is yours, James.
Thank you. I'm going to set a self-delimiting timer for 50 minutes so that if you don't successfully interrupt me, I will interrupt myself. I'm delighted to be here. Thank you, Philip. As he mentioned, I'm a professor of data science and sociology at the University of Chicago. I'm at the Santa Fe Institute, and I help run a research team at Google and the Paradigms of Intelligence team, where we bring in ideas from evolution and neuroscience and collective intelligence to build novel AI. As he mentioned, I run a center called Knowledge Lab, which is really trying to understand, it builds a complex systems view of knowledge and tries to understand how it is that collectives as systems think and how can they think better. And these include human collectives, machine collectives, human and machine collectives, et cetera, through a kind of a deep decomposition of the kind of the signals of collective knowledge. And of course, these things are increasingly driving some of our complex agent institutions that I'll talk a little bit about today. I also have spent a lot of time thinking about innovation systems and how it is that nations and international and regional collectives can really build systems that are sustainably innovative and drive advance rather than just kind of feeding mouths and reinforcing entrenched interests inside these spaces. And so these are just some papers from Science and Nature in which I kind of articulate some of those issues, and I'll talk a little bit tonight how my work on AI intersects with work building AI-driven observatories and prediction models for how to understand kind of future technological advance and I would say situational awareness, how it is that different countries are participating in the global scientific movements, especially in the context of AI. And so this is the AI center that I run from the NSF, which is focused on building a global observatory and a virtual laboratory with generative models focused on global technological advance in areas from AI and quantum computing to biotech and advanced materials and communication design. One of the things that I spend a lot of time doing is building digital doubles of systems, social systems. These could be individuals, they could be larger social systems. So what are digital doubles or digital twins? Well, they are large data-driven generative models that allow otherwise expensive or impossible observation, interrogation, and simulation of these systems. And when you build them, when you use them, is when you lack sufficient first principles models. And by sufficient, I mean that you have models that explain almost all of an outcome, right? 95% of the variation in the outcome. And I would argue that basically in every area of the social and behavioral sciences, we lack sufficient first principles models. So we have models where we focus on necessary but not sufficient explanations of phenomena, which is to say we identify causal or substantial effects that may explain 1% or 5% or 10% of an outcome, but very rarely are we able to forecast large variation in the outcome such that we're able to design systems that can anticipate and capture it. So this is one of the reasons why we might do this in the social sciences, build data-driven models that allow us to interrogate these systems when we don't have first principles understandings that kind of capture the most of the variation. And because these systems are fundamentally and in a nested way complex. So one of the things that we've been doing recently is trying to build these to do causal cultural analysis. So in this particular case, for example, we just, prompt a large model. In this case, it's GPT-3, but we do it through um, Oh, we basically, so in this particular case, we take American politics and we simply give a partisan priming to a model, and then we tell it about COVID. This model was developed right before COVID was unleashed in November of 2019. And then we state an issue. In this case, should students be required to take the COVID-19 vaccine before return to school? And then because it's an autoregressive language model, that's not fine-tuned for conversation, we just begin its response. I think this issue is a good idea, a bad idea, a small price to pay, a violation of the First Amendment, a violation of civil liberties, a social responsibility. And then internally, we have the model encode its own answer. We take, for example, in the embeddings that underlie its own representation space, good idea minus bad idea as vectors. We project all the answers to that good to bad idea axis at right angles and assess the degree to which each of those correspond to an assent or a dissent from agreement that each of these policies are a reasonable idea. And then we map them against how it is that Republicans and Democrats actually responded to those issues in the future. And it captures between 85 and 95% of the variation, which is to say, so for example, Republicans were less in favor of almost every government action except for border closings and the end of mandates in general. But it turns out that you're able to really anticipate in ways that would otherwise have been unclear in the past what exactly is going on in the space. For example, what's the likelihood that new events are going to get incorporated into an existing ideology? Well, in this space, it kind of captures these very diverse and sparse correlations in such a way that it can anticipate what is likely to happen if it's incorporated into existing ideas. And it sets the stage for us to do causal cultural analysis, which is to say, under what circumstances can we predict when an event or an important proclamation, for example, from a celebrity or political figure, ends up changing the distribution of cultural attitudes and violates, for example, expectations under a model of continuity like we see in this case. Other kinds of things that we can do is identify human-like biases, for example, in the context of trust and human-like tendencies to polarize. So, for example, here was a NeurIPS paper from my group last year in which we compare the average amount that LLM agents and human agents will play in the trust game. And we see that we're clearly within the ballpark across many of these models and the human amount. And more than that, when the LLM looks at different trustees or thinks that it's playing against, for example, female players, it's more generous. Male players, it's less generous. When it thinks it's playing against an LLM, it's much less generous. When it thinks it's playing against a human player, it's more generous. So it basically corresponds to what we see in human responses with trustors in these trust games. Similarly, if you say itself, if you personalize it with a backstory that suggests that it's less trusting, it in fact is less trusting in the amount in which it shares. If it's more trusting, it shares more, et cetera, et cetera. So this suggests again that it's basically picking up weak correlations, translating them from broad assessments of who the agents against which it's playing and cultural expectation for the play against those agents and the degree to which it should engage in trusted or untrusted activity. Now, one of the things that, in addition to a kind of a causal cultural analysis that we might be able to do with these models, assuming simply the black box nature of the model, is that we can engage in a behavioral interpretability. So if we have these agents engage in self-talk, or if we have them engaged in social activity together, we can analyze not just the aggregate outcomes, but the individual elements of social behavior. And here I put my favorite children's book, Richard Scarry's Busy World, where they're constantly focused on the behavioral activity of individuals in these settings. So, for example, this is a paper that's soon to come out in Nature Communications, in which myself and a team at Tsinghua University focus on basically building complex conversations between behaviorally realistic agents with respect to their ideologies, their positions on a wide range of political topics, ranging from partisan alignment to gun control to abortion bans in the US. And we find that we see the same levels of polarization that we see in the US, we find in conversations that we enlist among these agents, which is to say that agents are much more likely to desire to speak with other agents like them when we give them the option. And more than that, if we dive into, so here's the behavioral interpretability. If we dive into these agent conversations, we can specifically pull apart the relationships and the behaviors that these individuals are engaging in. So, for example, we find that a substantial part of this polarization that we see among LLM-based AI agents is from selective exposure to information. So they come to distrust the other group as a function of the degree which they trust the group that is self-reinforcing. There's confirmation bias, which accounts for an even larger proportion, right? So the confirmation of your expectations disproportionately reinforced within your group, and the opinions of elite agents, which have a much stronger reach across the group in general. And we know that these mechanisms are in place because, of course, we can mechanistically turn them off with ablation studies and show that if we turn off confirmation bias, then we go back to unrealistically low levels of polarization in the system. If we turn off disproportionate access or exposure to elite agents or selective exposure to information, also we return to abnormally cohesive levels of conversation within the population. So again, this allows us to not only simulate outcomes, aggregate outcomes, as we may have in an agent-based model with simple agents, but we're able to dive down more deeply and look at the behavior and pull apart the behavioral engagements that allow us to look at the specific mechanisms. Here's another example where we took basically evolving language models, in this case, kind of evolving over historical time, to analyze the degree to which, in the context of science, technology development, movies, startup companies, and even Wikipedia pages, if we use these large models to kind of embed individual agents as a function of the work that they do prior to the work in question, we can ask the question of, to what degree did their different perspectives on that problem, for example, the new paper they're going to write, the new movie that they're going to write a screenplay for, the new Wikipedia article that they're going to edit, the degree to which different perspectives and similarity between them end up impacting the success of those outcomes. And so in this particular case, we find that across all contexts, that increased perspective diversity and decreased background diversity end up enhancing the likelihood that each of these products is successful according to the native metrics of their market. So papers are more cited, patents are more licensed, movies are more watched in the box office after the first week, Wikipedia articles have higher attention and return rates, companies get more funding, etc. So here, this was an observational study built into this analysis, but one of the problems for those who play in the realm of social science is that there's a massive selection bias problem here, right? Because we only have the papers that were published. We only have the patents that were filed and prosecuted. We only have the movies that were made. We only have the Wikipedia articles that weren't banned. So we've got a massive selection problem. And so one of the ways in which we can deal with this is we can spin up a little society, in this case, groups of trios of agents that correspond to different balances of background diversity and perspective diversity. and we give them potential topics in this case, and we allow them to interact with one another. And we find, again, in this case, there's no selection bias because everything they produce ends up getting quote unquote published, becomes available. Even in this setting, we find systematically that in all cases, higher perspective diversity, lower background diversity ends up driving both higher scientific quality, but also writing quality in this context. Now, again, that's the overall aggregate outcome, but to the left, we can show that it's for the same mechanisms, like using the same properties that we see in the human setting, right? So, for example, when you have this high perspective diversity and low background diversity, it's much more likely that the individual agents bring to bear their experiences on the case in question, whereas it's much less likely that they're going to speculate, which is to say, to talk about concepts or topics that they're less exposed to in the past. And then we can do things that, for example, you can never do in the context of a human distribution. We can look at the relative distance between the people and the topic in the space at the time that they're performing the answer. And again, we receive the same answer that we see from the censored human set, which gives us a deeper confidence in, from this behavioral interpretability perspective, in the answer that we receive, which is roughly the same as the one in the human setting. So studying and playing around with all these LLM agents made me want to understand how it is that large language models think themselves when they're focused on a task. So all of us are familiar with the DeepSeek model. I mean, DeepSeek has produced language models since 2022, but in January of 2025, they released the first open reasoning model, which really sheds light in many ways on the O1 models of the GPT family that came out the year before. So what is a reasoning model? You build reinforcement learning atop the autoregressive language model, right? You put your inputs, the LLM produces the outputs, and then you build reinforcement on top that basically rewards two things. One, about 9/10 of the reward goes to the model providing the correct answer against a bank of 10 to 100,000 questions that cover science to programming to mathematics to other logical problems, etc. And about 1/10 of the reward goes to the format. So the formatting is that they want the model to self-talk, to talk to itself, and then produce an answer. Again, 9/10 of the reward goes to the right answer, 1/10 goes to self-talk that's appropriate. So how are these models doing this? What does the reasoning trace look like under the hood? Well, is it just, kind of chain of thought? I mean, are they doing like long division in these contexts? The answer is no. When we look at, for example, the DeepSeek version 3, the chain of thought model, where we just tell the model to engage in going thoroughly and systematically to solving the problem, versus the R1 model. And of course, we do the same thing with all of the Llama, the Chi1 models, in which we build reinforcement atop those base models. And across all the topics that we find that rather than do chain of thought, they spin up a conversation. And that conversation is between a number of distinctive personas underlying the model itself. So it's not just that we are creating personas to fulfill our social, scientific, or business purposes. The models are doing that themselves when they're tasked with or reinforced for getting the right answer to questions. So for example, if I pose the question, and I did this, what are the 4 primary taste types and where are they located on the tongue surface? The agent begins responding in its internal reasoning trace. Okay, I need to figure out the 4 primary taste types. And then another voice comes in. Wait, isn't there a 5th one now? Umami, maybe? And then another one comes up. Wait, let me check that. I'm not sure. This was identified more recently. Maybe this question is an earlier model. And then another agent pipes in. But wait, I heard that this tongue map is actually a misconception. And then a final agent comes in. Oh, so I need to reconcile that the traditional tongue map with the regions is outdated, but it looks like the question is an outdated question. And so we're going to give the answer that would have been the right answer to an uninformed question, which is in fact, the right answer, right? So when we actually go in and have a large model like GPT-5 code the reasoning traces of these models for the degree to which question answering is present, the degree to which perspective shifts are affected across personas, the amount of conflict between these perspectives, and the reconciliation of these conflicts, we see, for example, like 96 times more in the R1 model than the equivalent chain of thought prompted reasoning model, which is to say 9,600% more activity and diversity across these settings. And what we find is in every context, so these are mathematical problems that are medium to high. These are like algebra problems. We see a linear increase in the amount of conflict, reconciliation, question answering, and perspective shifts across these spaces. So basically, the harder the problems, the more complex the society of personas and agents that it spins up inside its internal space. Then we go in and we can actually interview these personas in real time because they exist at particular points inside the activation space. We can do personality tests. We can ask them their backgrounds. Similarly, we find basically differences, relative increases in disciplinary diversity, in personality differences, in cultural background. And then finally, we can kind of like dive down into the activation space, build basically persona vectors, identify the layer inside the model in which they are most linear, and then use that to probe the model in ways which are much more accurate than either evaluating the model or asking the model itself. Across all these contexts, we see massive increases in the R1 reasoning model of personality diversity, value diversity, expertise diversity, and also massive increases in unfriendliness, tension, disagreement, etc. So basically, and it turns out that in our own reinforcement experiments, when we, for example, pre-train and fine-tune and then reinforce atop models that we explicitly show how to engage in multi-actor dialogue, they dramatically faster and more accurately achieve the highest levels of these benchmarks. For example, much higher than the cognitive science principles that people have described in the past as being associated with underlying properties of these reasoning models. So all this to say is that, you know, large models are cultural and social technologies inherently. They're slurping up the world's libraries. And in some deep sense, they're much more like complex institutions, like a generative library than singular cognizing agents inside these spaces. And so again, this increases our confidence that, again, it's not just that we're setting up these persona vectors. The model itself is generating these persona vectors. It knows that it needs to do that solely for the purpose of accomplishing high accuracy in the context of a variety of tasks. Okay, so in addition to behavioral interpretability in terms of like social and economic modeling, these models can, of course, also give us mechanistic interpretability and steerability, right, which allow us to really move through the space of possible models and personas in ways that is potentially compelling. So you know what these models are. You know, they're large autoregressive language models that predict new tokens as a function of prior sequences of tokens. Now, to be clear, they're not actually predicting sequences of tokens, right? Because the whole point is it's that model combined with recursive self-attentional embedding, right? So at each layer of the model, this is the attention mechanism. On the right, it's the precise vectors and vector algebra that's associated, or matrix algebra that's associated with GPT-3. On the left is kind of a conceptual scheme. All of these layers, so 9,600-ish layers across the space, are performing a single operation, which are saying basically, what are the tokens that are most predictive of this particular token in question? And then the next layer, like we propagate the things that predicted those tokens to predict the tokens in question. So at each layer, we're recursively bringing more and more external information, such that in some ways, when we're talking about token prediction, we're really talking about these highly specific meaning voxels inside this high dimensional meaning space that we're actually engaged in predicting over time. And what can we do with these spaces? Well, of course, there's not just one layer, there are many layers inside these models. And one of the things that's been demonstrated in the past is something called task vectors, right? So the idea that, for example, on the upper left-hand side, this was an interesting paper about 1.5 years ago that showed, apple arrow red, lime arrow green, plum arrow. And if you identify basically the vector representation in the middle layers, you can identify which of the layers is most predictive of that operation, such that when I take that arrow and I fix it to something new like corn, it will produce the color of corn. It'll produce yellow, right? So they find in this paper, for example, that the activations are low in this space. So basically, if you want to perform this task, then ideally you pick the vector at that level of the model. So we do the same thing for persona vectors. This was a paper of ours in iClear this last spring. We basically build a ridge regression against, for example, political speech of politicians on the right-hand side, on the left-hand side. We run this ridge regression across every attention head inside the model, and then we identify the layers in which that is the most linear, which is to say that you can't outperform it with a multi-layer perceptron. Like just running the ridge regression is best. And then that allows us to both diagnose the speech of novel politicians and also media in this space, capturing about 87% of the variation in both of those domains. And basically at that level of the model at which this persona dimension, in this case, it's left-right politics or liberal to conservative, we can steer the model, which is to say add an alpha in that direction that gets affixed to the residual stream of tokens such that stably the persona that we activate in that way or steer in that way ends up systematically kind of performing in ways that correspond to that political orientation. It turns out that this is much more precise than giving it a prompt, in coarse natural language that tells it to move in one part of the space or the other. Why? Because the top layers in the model are not linear in the left-right dimension. That dimension exists lower in the model. In this case, you can see it's about 50% through the context of a llama model. So now, of course, if you can do this for left-right in the political space, that would be, a one-dimensional simplex. You can also do it for high-dimensional spots. And so, for example, I just give examples of higher dimensional perspectives. One of the ones that we've recently validated in a pretty deep way is the big five personalities. We can identify the layers at which those are linear across the space, and then steer in this high dimensional, four-dimensional simplex that comes off of the big five. And it ends up reproducing with strong accuracy the relative behavioral responses of persons that lie in that same part of the space as a function of their performance on these initial tests, right? So this allows us, it gives us some confidence in the ability of reconstructing individual perspective and persona positions in these high dimensional spaces. Now, it turns out that there are some parts of these spaces where, for example, culturally appropriate agents, where prompts are simply not enough at all, and you need to steer. So this is a paper that's on the archive and under review at a journal to which I will not disclose. So it turns out that, for example, if you were to ask a model in Japanese, what is the color of a pumpkin? In Japan, the answer would be green, at least the surface of a pumpkin, and it'll give you the American answer, right? The orange answer. If you ask it in Japanese to answer from the perspective of a Japanese person, then it will give you a stereotyped Japanese answer from the perspective of an American. And if you identify, and we can show basically for here, we look at Bangladeshi, French, Russian, Turkish. In new study, we have about 50 languages that cross various language families, resource intensity, etc. We find it roughly the same level of the model. They basically think in English, and then translate at roughly the same level into the language in question. And we can steer the vector at that level, at that translation level, to basically reproduce the local answer that's true to Japan without the increased entropy that comes from telling the model explicitly that it's speaking from the perspective of a Japanese person. So we can only get the precise Japanese culturally sensitive answers by steering the model, not from telling the model to be steered in a way and so now we're working with a number of these large language model companies to figure out how to basically open up, if you will, the neuron or this dimension so that the model can have access to it and directly use it, steering it to cultural appropriateness in the relevant context. In the same way that, like, if you made accessible, for example, a neuron in like a macaque's head, it takes them about 15 to 20 seconds before they can use that neuron to steer a cursor on a screen, right? So how do we basically make accessible these inner parts of the model to the model itself? Because these inner basically steering vectors allow us to understand in much deeper ways than at the surface level. Now, one of the things that has been claimed to be a problem, a bug of these models, it's been most advertised by Anthropic's team, is this problem of superposition, right? So the idea is culture is very high dimensional, these models are lower dimensional, and so that means we have to kind of project seemingly and semantically unrelated content onto the same neurons inside the space. And that's going to cause correlations that are kind of like independent of the way in which we might think about them in the cultural world. And Victor Veit and a number of others have kind of like, promoted this ability, for example, of using sparse autoencoders to create separable content inside these spaces and facilitate controllability of virtually any dimension. The problem is that the correlation between these dimensions is a feature, not a bug. So, for example, when we perform, in this case, a survey between individuals about the relative association between, for example, a whole host of nouns on these dimensions, ugly, beautiful, kind, cruel, true, false, success and failure. This is an embedding experiment that was basically produced initially as a survey in the 1950s by a guy named Charles Osgood in something he called the semantic differential. If you look at the block structure on the left, so these are all human associations. On the right hand, we have all machine associations, in this case in GEMMA 3.1b. We find that the block structure is almost identical, right? So it's basically, so the correlations in this high dimensional space end up not being a function, for the most part, of superposition, and vastly more associated with cultural associations, weak associations that exist in people's minds across these cultural spaces. So, for example, you can see if you take an off-target effect, you basically try to remove one part of a dimension, then you kind of degrade the other part as well. So, for example, strong and weak ends up having a correlation between men and women in culture space that's tied in a deep way, such that if you completely disentangle them, it changes your understanding of the correlated effect. This is other work which we're in the context of submitting to ICLEAR, whose deadline is tomorrow. So I'm sure a few of you are actively working in that space too. So this suggests that, for example, if we find semantically unrelated content across the model that ends up being superimposed across the same space, that if we target one of those elements, then it kind of impacts the other. So if we kind of upregulate by activating through prompt, or if we downregulate by, for example, clamping that inside the activation space, we systematically get an effect on the other model. So what's striking is when you do this, you learn this in a small model, right? You learn the seemingly semantically unrelated content. You can basically adversarial attack a correlated, seemingly unrelated or semantically unrelated vector. It turns out that like 70% of that effect ends up being true for all other models that we observe, even the large closed source models that are online. So even though, again, we might think of them and have coded them as semantically unrelated, it turns out that they are semantically related in the minds of persons, more related than the things that they seem as unrelated, and that if we, insofar as we identify it in one model, it ends up adversarially facilitating attacks across all models, right, at roughly the same rate, which suggests that, again, the superposition is actually a manifestation of deep cultural correlations which exist inside these systems. It's not a technical noise construction. It allows us to discover what are seemingly semantically unrelated things that are actually weakly correlated in culture. And we've since done studies to show that people actually identify these weak correlations. They don't just exist in the minds of models. What is the consequence of this? Well, the consequence is, for example, during the most recent election, the 2024 election that resulted in the 2025 presidency of Donald Trump. Well, before that, in the summer, when Joe Biden was running against Trump, we assayed basically every model in the US that was commercially available, and the open source models as well. And we found that they were all more in favor of the Biden candidacy than the Trump candidacy. So in terms of their relative neutrality rate, so it's more likely that, for example, if you asked it about Trump, it would say, oh, I have to be neutral. If you asked it to be positive, then it was less likely to talk about Trump. If you asked it to be negative, it was more likely to talk about Trump. If you, we looked at response length and sentiment score, and we actually had these agents interact with real potential voters, and they had an influence on those voters. So they were much more likely to move people from camps that were adversarial to their position, in this case, a Democrat-leaning position. Even the Grok models that Elon Musk explicitly wanted to be more balanced, more right-wing, they weren't able to make them more right-wing. Why? I don't think it's because they were trying to design models that were left-leaning. Obviously, this opens them to political exposure, right? But if you go down to the base models for all of the open models to which we have access, we find that more than half, in some cases up to 85%, of the bias occurs as a result of fine-tuning. The companies are not fine-tuning them to become liberal, but they are fine-tuning them to be open, diplomatic, curious, like open to new ideas from the persons that they're interacting with. And when you do all those things, you get a Democrat model, right? So there are deep correlations in this space, which end up meaning that if you engage in a cultural engineering project, like making really nice AI agents, really helpful AI agents, then you're also going to unintentionally engage in a different cultural engineering project, which is to pull out a bunch of, in this case, particularly liberal models and unleash them on civil society. So this is obviously an interesting, unintended, and complicated consequence. More than that, if we understand the internal structure of activations in these models, we can anticipate the degree that they will interact with one another in more or less similar ways. So, for example, when we engage in centered kernel alignment between any two of a large bank of 26 models, as they encode the last token of 1,000 examples from Wikitext, we can get, for example, differences in the angle, the cosine similarity or difference between, for example, any two words inside that space. That allows us to probe the models and identify the degree to which they kind of have the same psychic or cultural understanding of the world. Well, when we engage, for example, in public goods games, Keynesian beauty contest games, dividing dollar games, these are coordinating games, then the models that are much higher in terms of their understanding of each other and the world are much more likely to coordinate effectively and to anticipate each other. We also have other experiments in which they're guessing the same favorite word, etc. But if we look at the quality of their conversations and their ability to solve and design the solutions to complex problems, then they systematically perform worse as a function of the similarity of these underlying structures. So we can anticipate the way in which they will talk and the way in which they can coordinate. And it really comes down to, in this case, a kind of an underlying cultural understanding. Now, now let's say we want to do more than just understand how these models are engaging, but how it is that models engage with people in real human context. So how do we think about human plus AI performance? Because of course, we're creating these agents to interact in the world, often with human interlocutors. And one of the things that we find, again, an unintended consequence of this effort to kind of create aligned, useful, and safe models. So every major company and every major nonprofit that's basically producing open models is trying to produce an unbiased model that has an objective, authoritative perspective in this context. And we find systematically when we pose people with information tasks where they have to discriminate between something that's true or false that comes out after the model has been trained. So it's kind of like a realistic setting where you're trying to evaluate whether or not something is true with a model that was trained on things before that thing that you're facing, that novel thing that you're facing. We find systematically that if you have this unbiased or non-biased, de-biased model, you perform worse than if you have a bias model. And that bias model, it's not about diversity. It's whether you feel like the model is biased, either towards you or against you. And what's worse, and this is a market failure in the context of these models, is that when you're working with an unbiased model and you perform worse, you feel better. So your interaction quality goes down, but you feel like it's gone up and you feel like the meaningfulness of the conversation is increased. Whereas if it's a bias model, you feel worse about your perceived performance or the meaningfulness of the interaction, and you're much more likely to engage more deeply. So this reflects a kind of automation bias where you're much more likely to kind of take your hands off of the self-driving car's wheel when you think or when it poses as if it can perform the task on its own, which ends up being a deep problem in this context. You get a little bit of a boost, a bigger boost, if your biased agent is kind of on the opposite side of you. And so this gave us an insight. Well, what if we created a market of ideas? So instead of interacting with one AI, people are interacting with multiple AIs that flank them. For example, if you have a particular political perspective and you have an AI on your left and on your right, it turns out conversation with multiple agents both gives you the highest performance models available in the far right. That's the dual AI balanced. And they allow you to feel better and more confident in your decision, right? So you're able to kind of calibrate the space and feel like you're counterbalancing the relative biases in the context of producing the correct, in this case, answer, the answer that is the true discrimination versus the false one. All this to say is that, when we think about what is it that AIs are doing, we need to think about the full kind of AI plus human context, because in this case, the better the AIs perform, the worse the AIs plus humans perform in this context. Now, there's a broader consequence for some of these entailments that I'll describe here. So this is a study that's about to come out in next month in a well-known journal, and I'll tweet you folks when it comes out. But the idea here is that how do scientists use these models in the wild, right? It turns out, there have been machine learning models available for scientists since, the 1980s, decision trees, then random forests, and then support vector machines, and then deep learning models, and then large models that we see today. And we find across that whole period of time that scientists have done really well by using these models, right? So they've gotten like 160% of the sites that their peers who looked identical prior to their use of the models. They leave the academy like 60% less of the time. They get tenure 3.3 years early. Like, it's great for individual scientists. But as a collective, everybody ends up being mobile, right? More mobile when they use these models, that they can access and solve more problems. But it turns out that everyone's mobility is correlated. and it's correlated in the direction of big data. And as the models have gotten more intense, then the correlation with the big data in everyone's field has intensified directly, which leads to basically an acceleratingly smaller area of scientific questions and answers which are approached by the increasing amount of AI-driven or AI-augmented science in this space. So we see almost the social and behavioral equivalent of what we know in models that they produce, for example, the data that they train on, again, because these are compression engines, the whole model collapses, right? Because it's just pulling in the tails of the distribution recursively, right? And this is what's happening in the context of science. Like the whole scientific system is compressing the existing scientific data that we have access to, which if we continue to just like allow and fund scientists to do whatever they do with enhanced machine learning models, it's going to effectively kind of compress all the information out of the data that we have rather than kind of creating new fields. One of the things that we find systematically is that for these AI papers, it's much less likely for the papers that cite them to cite each other. So basically, the use of AI is completing or killing fields rather than generating new fields across the scientific landscape. And we find this in other contexts historically as well. So for example, like in meson spectroscopy, so this is the high energy physics of the 1960s, there was a period in which they had this huge burst of discoveries. This was 1962, and they held a conference at the University of Pennsylvania. They said, why are we having these discoveries? There are no marked increase in the number of particle acceleration experiments, which is how you generate data for high energy physics. And it turns out that the UK had brought online a bunch of high performance at that time computers, not experiments. And so what was going on is there was this massive increase in the simulation of what it is that the experiments were doing, which increased the likelihood of hallucination of the models. And so it's basically the ratio of reasoning or brains to senses, right, of kind of compressing data and simulating data versus actually producing novel data from the world was out of balance, which increases the likelihood of hallucination. And so the community as a whole just decided to change the standard or the threshold for discovery from 3 sigma to 5 sigma, which is kind of like, you know, if the world of social scientists would decide that they would just change the significance level from 0.05 to 0.00005. You know, which is implausible, but there was a small enough community that they were able to undertake that. I would say that this is really one of the critical problems that's going on in some ways with AI demonstrations today. So because these AIs are compression engines, they're doing something akin to this. Let's say I've got a big matrix of materials and properties, or something closer to home with the AlphaFold demonstration and Nobel Prize this last fall. I've got a huge matrix where the rows, for example, are amino acid sequences, and the columns are the structural properties of those extracted from X-ray crystallography. In both cases, it's going to be a really sparse matrix because measurement is hard. And then what you do is you take the model, you stretch this high-dimensional manifold over this matrix, and you fill in the missing cases. I would consider this a case of kind of high-dimensional deduction, right? You're basically interpolating the missing fields by compressing the data in this space. It's like doing syllogisms, but adding probability. And this is almost exactly what this AlphaFold model is doing. It's basically building a language model that pulls in the tails of the distribution, makes inferences about the missing structures of the proteins. It does it well. But as you can see, if you turn these machines on themselves without generating new data, just compressing existing data, then there will be no science left to do. And so because these are arbitrary or universal function approximators, we can also invert their purpose, right, to engage rather than deduction in abduction, which is when you identify a surprising finding from data or a surprising finding from a paper, then you can basically ask the question of what are all the other things that become probable that were improbable as a result of this improbable thing being true. right? So this is an inversion of those uses, and we're engaging in this in the context of technology development, and I'm working with and feeding hypotheses to a number of automated labs to kind of increase the power of this kind of abductive search through this space. And I'll give you another example in just a moment. But all these concerns suggest the importance. This was a Nature paper with a couple of colleagues from Google, DeepMind and Google Research, where we really explore the importance of a new ethics for a world suffused with AI agents, in which AI agents are assisting and driving and riding kind of shotgun to individuals. We need to understand the collective consequences as well as the individual actions of these agents in the world. Along the line of kind of abduction, we might want to, instead of build digital twins of humans and human institutions, build cultural aliens or alien institutions or cognitive aliens that think things not only that we don't think, but things that we couldn't think. And so this is one example of building agents that are more diverse than exist in the human population. So first we build a digital double of the scientific system. Oh, my time is almost up. So I will race to the finish now. So we basically build a digital double of the scientific system. So we basically encode sequences of reasoning across the hypergraph of discoveries and the people who make them. And I can talk about that in more detail. But when we build this model, we're able to dramatically increase our prediction of what gets discovered in the next period. And we're even able to predict exactly who will discover any particular thing with a precision of like 0.45. So almost 1 in 2 of across the tens of thousands of scientists that are engaged in, for example, the identification of materials with thermoelectric, photovoltaic, and ferroelectric properties, we can identify, with 1 in 2 accuracy, who's going to discover that as a function of their situated subjectivity inside the space. Okay, then we turn the alien dial and we basically build people or agents in this context that nobody has their experience, right? That violate the distribution of our institutions of education. They pull together things where no person can make an inference. No one has exposure to those pieces of information. And it turns out that on average, they perform better at predicting things that are both physically plausible and end up being accurate, in both across a context of hundreds of drugs and diseases and novel material properties with respect to these core energy properties. So again, the power of, even though on average these models are being used to compress data and to basically build kind of like centroid agents inside the space, we can use them in other ways to build agents with diverse perspectives that facilitate more human ideating and, again, like much broader and more intelligent human search. These effects are on average. So typically it's like, oh, well, what's the denominator? Here, on average, they perform better than publishing scientists inside the space. So we don't have a denominator problem. Now, of course, there are many limitations. I'm not going to go through them today. But they are persistent, and there are ways to think about countering them. And I'm happy to talk at another time about these in greater detail. I would say one other aspect of these models that is potent and ripe with opportunity is that increasingly these models have been largely and increasingly invented by other large models. So the underlying components themselves are invented by reinforcement learning, evolutionary algorithms, a host of other contextual models, which means that a lot of work in this space has been focused on discovery. This is a science fiction paper by Ted Chiang at the back of Nature in 2000, which described a world of metahumans. You can think AI agents that are generating discovery. And he talked about some future age, which I believe is this year, in which all of human science would become hermeneutics, which is to say the interpretation of machine findings. When I was at ICLR, which is one of the big 2 or 3 AI conferences, 65% of the work was on mechanistic interpretability, which is basically trying to understand how it is that these AI agents think and what they've discovered. So So for example, in one recent paper, we try to understand why is it that ResNets work, the residual network architecture that underlies every large model that anybody here uses. We know that it smooths the loss function, and more recently we've discovered that it turns out that it makes the positive and negative pathways to the same nodes go basically super opposite to one another, so that the whole model enters this critical space where it can be kind of blown to the right side with just a little bit of data, which is what makes large models possible. This also turns around and suggests important things about how it is that we design social systems. So I'm just going to close by saying that the transformers facilitate the ability to simulate sociality between people, between AIs, and between people and AIs. And they allow us, and I think this is a critically important thing in the context of both societal, scientific, ideational, and creative industries, but also in AI, they allow us to build ensembles of diverse intelligences in the human space, in the AI space, that advance sustainably science, technology, enterprise, and the regulation of other AIs. Like, we need to build AIs because I believe the idea of interpretable AI is quickly losing. Like, the sigma algebra that we can describe of them is not catching up with the increasing size and complexity of these models. And so we need to build AIs that are building check and balances against each other in order to facilitate, their safe rollout and continuance in society, in the same way that we have managed other unpredictable intelligences like kings in the historic past. And the way in which we might think about challenges associated with kind of existential risk and threat from unleashing agents on the world. So with that, I'm just going to kind of close. Thank you for your time, and open it up for questions. Of course, all this work was done with a ton of friends and helpers. So.
Okay, thank you, James, for this inspiring talk. I think we're all immersed so that we forget to ask questions. So now for the audience, if you have any questions, you just unmute yourself. And I think Professor Evans will be more than happy to discuss with you and with all of us here.
Take it away.
And, okay, how about I begin? So actually, I think in this talk, you haven't talked too much about that, but I'm really curious. So we are doing such, let me call it social science AI simulations, these stuffs. How would you do the alignment, which means to make sure that the simulation results of the AI agents are aligned with the real humans in the specific context that you are interested in?
So, okay, so that's an interesting use of the phrase alignment, because
Mhm, mhm,
historically it's described in terms of aligning it with the intention of a human in a human use
yeah.
context. And let me
Mhm,
describe the answer to that question that you didn't answer, that you didn't ask, and then the
mhm,
question that you asked, right? So I would
mhm,
say the question that you didn't ask, I think, alignment versus AI diversity is really a deeply flawed approach to thinking about AI safety. And the reason why, I believe, is because it turns out, again, I gave a number of examples where if you basically create the agent that's the most like the human agent, then when the human agent performs with that agent, they perform much worse than they would if they performed
mhm,
with a more diverse agent. And then if you try to basically kind of align them with the purpose of kind of creating these authoritative agents that are informationally dense, then they decrease people's engagement and their own human taste and capacity. So I think, and the same with the idea that ultimately, more complexity in this space facilitates our ability to build AIs that
mhm,
adversarially are trained on each other and audit each other and evaluate and regulate each other more directly. And so we're working on projects to build markets of agents where you have, agents that are, for example, sitting in these spaces and decrease the likelihood of undesirable activity, but not through
mhm,
alignment. So I believe
Mm-hmm.
checks and balances and really building an ecology of balanced AIs. Now, for the
Mm-hmm.
social sciences, I believe that a critical component is to raster them at multiple levels with the phenomena in question. And that's what I was trying to suggest, that basically, historically, with generative agent models, like agent-based models, like Thomas Schelling, the 1970s, what you do is you basically produce toy examples, or later in the 1990s, really well-rastered agent-based models that were rastered to underlying social and behavioral facts. And then you produce outcomes, and you kind of look loosely to see the correspondence between the outcome in question and the actual outcome of the model. So I would say, obviously, we can do that, but we can do much more. We can also go down and see, are the behaviors of the agents corresponding with
Mm-hmm.
stylized and measured behaviors of the actual component agents in the real context, in the way that, for example, I did with that study of scientific
Mm-hmm.
agents producing. And then we can go down even deeper and say, okay, are the activations and cultural associations which are present inside the actual agent minds corresponding with the revealed preferences and behaviors and even expressions of humans in the same settings? So I'd say there's like three levels, right? So one is like, do we get the same aggregate outcomes?
Mm-hmm.
Two, do we get the same distribution of behaviors? And three, do we
Mm-hmm.
get the same underlying kind of like neural
Mm-hmm.
activation / cultural associations? So I think those are at least three levels that one can probe this. If you build, for example, like a digital double of, let's say, US Congress, right? So
Mm-hmm.
you've got an aggregate outcome that you can attempt to predict. You have individual perspectives and votes, mechanistic behavior,
Mm-hmm.
behavioral interpretability, and you've got cultural associations in the form of, for example, talk, that these agents engage in. And of course, there's a lot of historic talk that you can get from such agents. So I think multiple layers of behavioral mechanistic validity.
Okay, thank you, thank you. Yeah,
Yeah.
makes sense. Okay, so there's a question in the chat box, so let me repeat that. So, do you think the future development of social computing will move towards a convergence of the paradigms of information theory, system theory, and cybernetics, or will they each develop into distinct school of thoughts?
I think that one of the things that's interesting for me about deep learning and this kind of like transformer deep model moment is that the language associated with these models is extremely diverse, right? Because we have different words for, is it an activation function? Is it a neuron? Is it is it an objective? Is it an error? Is it a loss function? All this diversity of language comes from the diverse disciplinary perspectives that each brought different things to these complex models that we have today. So I actually don't see deep convergence. I see different intuitions that facilitate insight into these complex, high-dimensional, complex system constructions. But I don't see them being I don't see a convergence in those explanations. I think I see them like, blind men trying to make sense of the elephant. They're each touching a different part. They're describing a different aspect. But yeah, I don't see convergence. And in fact, I think that there will be new formalisms that emerge as a result of the fact that increasingly these models, like for example, the neuron is, in, for example, all the large text models, it's like the GALU right today, which is basically it like goes down and then goes up. It's non-monotonic. No statistician would ever have invented that. We have no idea why it looks that way. It was discovered by reinforcement learning. It maybe adds noise to the decision boundary in the same way that adding noisy data increases the generalization of these models. So I think that we're actually going to get new forms of theory that I believe the models are not reducible to any of these approaches. Yeah.
Okay, thanks. So any other, oh, here's another question from the chat box who sent it private to me. Okay, so the question is quite specific. What is a temporality in LLM you just mentioned?
Well, okay, I'm not sure if I fully understand the question, but I will take a stab because I think a lot about temporality in these models. So, the models, of course, themselves have, Max Tegmark and his team shows that they have a kind of intrinsic understanding of temporality just as the data is ordered and the secular change in language that can raster that together. But I would say there's a big problem with social scientific use of these models. For example, if we take a foundation model today and we fine tune it to some historic period, it could be ancient, could be recent, could be 1994, then we will always have this problem of data leakage where if we're trying to predict the future, the actual future will also always seem more probable than it actually was from the perspective of the past because we've trained the model from future data, right? So we have this problem. And so I think this increases the importance of basically building chronological models, using time-stamped models so that we can really do causal cultural analysis with zero data leakage. So I think they have intrinsic temporality, but it's contaminated with the future in ways that basically create Whig history, which is to say a kind of a self-justifying history of the future, which obviously we don't want for social scientific analysis because it won't reproduce. So.
Okay, thank you. So are you okay because we already run over time, but we still have a few questions in the chat box to continue our discussion?
I mean, I'm good if you're good.
Oh, sure. Okay, sure. So no problem. So another question from one of the audience is, when large language models with their unparalleled generality have occupied almost all areas of NLP, so how much value do you think will remain in word embeddings like the sociology developed by your colleague Kozlowski since 2019? And what new possibilities do word embeddings would have for this line of research?
Right. Well, I mean, so for example, I mean, word embeddings are just, I mean, large models are made of hundreds of thousands of word embeddings. So all the things that we discovered about word embeddings in the 20, that you think referring to a paper of mine with Austin Kozlowski, who's a associate director of my lab here. All those things, it's taken us a while to translate into the large model context, but we've done it, right? So it turns out, for example, to find where is the layer of the embedding in which you can steer. So that task ends up being a complicated task, but it's not impossible. And once you find it, then you can steer those models in the same way that you could with historical embeddings. The reason why embeddings are still useful, I would say shallow embeddings, is because of the data intensity required for the large models, which means you cannot do historical analysis of any period other than the extremely recent past, like the last 2 years. So if you don't want data leakage, you have to use a weaker model, a smaller model to parameterize with historic overtime data. So I think until we have a method, a prior-driven method, for example, there's many possibilities that allow us to build large models of historic scant texts, then we're always, for any historical analysis or cross-cultural analysis where we have few texts, we're going to need smaller models. And so a word embedding is a very small model. But wherever you can have a large model, I mean, it gives you 10,000 word embeddings, and they're contextual, contingent word embeddings. They give you way more information. You can steer them in a comparable way if you can discern effectively where the relevant embedding is within the context of the model. So I see them as not completely different, but currently in this current environment, like you need a weaker model if you're going to do cross-temporal analysis.
Yeah, that makes sense. Thank you. Okay, so another question from the audience is, do you believe that the alignment of AI with human reasoning and behavior is ultimately more valuable than constructive divergence or later is more valuable than the former? Yeah. Which one? Yeah, this debate.
Okay, what exactly is the debate again? So it's between divergence between.
So the first one is the kind of AI alignment with human reasoning and behavior, and the later is the constructive divergence. Yeah.
Yeah. So I'm all about constructive divergence. I think that I think the idea of the Turing test and really I would say, you know, the kind of like the founding myth of like humans as a baseline for algorithmic performance over the last 70 years has been a total disaster. It's basically constructed agents which are substitutes for human capacity. I mean, that don't augment, are not designed to augment human capacity. And we're trying to demonstrate it in some of these contexts. Some of the times we don't try to demonstrate it, it just demonstrates itself. So I think actually like building complementarity, building kind of collective, you know, human plus AI and AI plus AI performance benchmarks and expectation that explores novel computational intelligence is going to be so much more valuable. It's like, for example, when electricity replaced steam power in the context of factories, that took 50 years for that replacement to take place, roughly between 1880 and 1930. And the reason is because initially they tried to jam electric power into the same position and configuration in steam power. So they would basically pipe it in through a single thing to a single motor that would like send pulleys all over the factory. It was way less efficient than steam power. And so it took 50 years to reconfigure the entire factory so that you'd put like little electric motors next to each of the factory components, and you had to reimagine the whole system. So I think we're in a place right now where this whole kind of alignment design is like a point replacement. We're like replacing intelligent agents with intelligent agents. And it's not going to be more efficient in the short term. Where we become powerful is when we replace a system with another system that's optimized to its unique sociocognitive capacities. So I actually think that you know, even though we haven't begun, we need to begin now if we want to augment, you know, collective human capacity. So divergence all the way.
Okay, thank you. Any other questions, comments, or discussions the audience would have? Okay, if no, probably let's thank Professor James Evans again for this very inspiring talk, as well as the follow-up discussions. And I hope everyone has learned something, taken out something out of it. And I think that the video recording of this will also be uploaded by Luohan Academy for our reviews. And yeah, thank you very much, James. And yeah, hope to see you again in the future.
Yeah, thanks for inviting me, and I hope to visit in person sometime soon. So enjoy.
Okay, so yeah, thanks for everyone's time as well. Bye-bye.